Right, so this is a quick ramble for about 3/4 of an hour about the CubeSat projects in general, more specifically FUNcube. Started out about 4 years ago with a few ideas that we were banging around. I've been involved with AMSAT for about 30 years now. North American version, and we have a UK version. And there's about 15 AMSAT organisations around the world. The biggest problem we have is international agreements between the organisations, because the US are very reluctant to give their ideas out or their intellectual property. They considered a satellite to be a munition. So it's subject to the International Trade in Armaments regulations. So up to about 15 years ago, our US colleagues were talking to us quite happily. And then some of them got caught by ITAR and almost got put in prison. Seriously, the FBI were involved. So they had to make representations through legal means to say what they'd said to the rest of the world. And basically they were given a rap over the knuckles because it wasn't commercial information they were giving away, but they shouldn't have done it. But they actually wouldn't say what they shouldn't have said. Go for it. More recently, the US regulations are changing, so hopefully they won't be subject to ITAR, and we can do more cooperation between the groups. Anyway, that's just the background to what AMSAT's all about. The rest of the world all talk to each other. We talk to our German colleagues, our Australian colleagues, our South American colleagues, and we can tell the US what we're doing, but they can't tell us what they're doing, unless it's something in the public domain in a presentation. Right, so AMSAT-UK has been around for about 15 years, and we've been funding other organisations around the world, buying solar cells, buying batteries, buying pieces of hardware. And we've got something like £100,000 in our pot for satellite subsidisation. 4 years ago we decided, can we do one ourselves? If we can we do it on the cheap? Can we do it simply? Can we do it KISS? We answered all those questions. Yeah, of course we can. We were very fortunate that we received legacy of about £40,000 about 4 years ago. Subsequent to that, we received another legacy of an equivalent amount. So we've had about £80,000 in money put into it. In terms of the amount of effort that's actually gone into it, we reckon it's about £250,000 in terms of man hours. And that's about right for the satellite of this size if somebody had to go out and buy one. The other thing we've had to do is actually raise funds for the launch, because they aren't cheap. It's about £100,000 a kilogram to get something into space. I'll say more about that in a minute. So we had to decide what we're going to do with the satellite. How could we make it popular amongst the general public? So we decided to look at STEM, science, technology, engineering and mathematics. So that was our outreach. We also had to be an amateur transponder. And we needed to find a team of volunteers who would actually step up to the mark and be still with us in 4 years' time. Well, I'm one of those, and there are 6 others. Various skills, RF engineering, software engineering, microprocessor engineering, and hardware, from a variety of companies, all given their time for free. This is me from Black Pepper, and a couple of guys from BT Research, and a couple of guys who are independent contractors, and we also have another part of the organisation. Bottom there is called AMSAT-NL, AMSAT Netherlands. It has a membership of 1. And the reason why it has a membership of 1 is because this is actually a Dutch satellite rather than a British satellite. Because of the legality of UK space law, we had to pay £20,000. We would have had to pay £20,000 up front, probably more than that, to actually apply to have a licence to put something into space. Once we'd done that, we had to raise something like £5 million per year insurance to have something in space. That wasn't tenable with a small organisation like us. So we asked our Dutch friends, would they take it on, because their space law is completely different, and they said, yeah, okay. So they actually bought the rights to the satellite for £1. So this is actually a Dutch satellite. Primary objectives. The stated aim is it's educational outreach. I'll tell you more about that in a second. STEM projects are radio, electronics, physics, mechanical engineering, and orbital mechanics, which is what my sort of skill is. And a science payload. Basically, in space you get radiation from the sun, and it's surprising how much there is, but how little temperature differential there is in the satellite because of it, even though it's putting out many petawatts of energy. We are transmitting data, about 40, it says 40 telemetry channels, it's actually about 54 telemetry channels we're sending. Electronics, it's a stack of about 7 boards inside the satellite, I'll show you in a second. So it's all the interactions between them and all the protocols to talk between all the boards, so we've had to design that as well. Trying to get kids involved, well, everybody knows about Twitter, so how can we name it slightly different? It's a FUNcube Twitter message, so it became a fitter message. Oh, God doesn't know why we changed that name. It seemed like a good idea. And it takes short greeting messages of about 50 bytes, something like that. And the spacecraft transmits within the amateur radio frequencies, otherwise known as the amateur space assignment. It's going to operate in 2 modes. The idea was if it's in daylight, we want it to transmit as much power as it can, so a school can pick it up with limited antennas and receivers. They don't want to have to point it at the satellite and know exactly where it is in space. You want to stick something on the roof with a little amplifier and get the signal. So in sunlight we're putting out about 310 milliwatts of power. During the night, or in eclipse, when all the schools go to bed around the world, it becomes an amateur radio transponder, and we call it a bent pipe. So basically you transmit up to it, and it transmits back again. But it's not just to you, the footprint is transatlantic. So you just about manage New York from here, if you've got good antennas and you're pointing in the right direction. I'll tell you about pointing in the right direction in a second. Carry. So we had to, because we're pointing it at schools, that was the initial intention. We didn't want to have to go out and buy a really expensive radio and something that they had to track with. So we came up with something called a FUNcube dongle. And as you can see, it's a USB device at one end and an antenna sticking out the other end, screwed in. And it's about big. Software-defined radio. I'm not going to go into SDR in this thing, but basically it comes out as a USB sound card. So on your PC you just see a sound card presented. The audio comes out in baseband. We also have a tuner which has been developed. This version on the image is the Pro Plus version, so this is the second version. The reason why it's the second version is the chips we were using on the first version went out of manufacture. So we had to re-engineer this very, very quickly. And in doing it, we've increased the bandwidth, we've increased the performance quite a bit. So we're very, very happy with this second version. And we sold 10,000 of them around the world. I mentioned that the launch cost is quite excessive. All the profits from this have gone towards the launch cost. So the guy who designed it is taking his manufacturing costs and so a bit of profit, but all the excess cash is actually going into the launch. And he says, trying to explain to his accountant why he's buying a Dnepr launch. It's very difficult. He's done it. So this is the guts of the FUNcube dongle. It's a 24-layer board. It started out being 4-layer board in the original version, but this is quite complex. And the big blocks on there, particularly the one that's there, it's quite a smart piece of kit. We're using what we call surface acoustic wave filters, SAW filters, such that the satellite is intended for a 145 megahertz downlink, so the SAW filter is actually centered around that. But it is also a wideband receiver, so it cuts out the noise around where the school will be receiving it. So we've tried to optimise it a little around that. I'm not going to go into too much. This is the set of slides we tend to use at radio clubs, so they're more interested in the electronics. So I won't go into this too deeply. There are a set of boards on the satellite. This is the command and control and telemetry board. We use the guts and the I2C, which basically communicates all the data between the boards within the satellite. It's a well-known protocol, but it's not well documented. So people in the electronics industry know about it, but we sort of came along and went, oh, why is it ringing? We're getting all sorts of strange data on the bus, so we fixed that with a few pull-up resistors. The supply on this satellite is either 3.3 or 5 volts. So it's actually quite low voltage. And the biggest problem you have on something that's only sort of 10 centimetre cube is you've got solar cells on 5 of the surfaces, so you're not generating a lot of power. So everything that's designed within the satellite has to be power sensitive. So on this, you're only drawing about 15 milliwatts, and the peak power is 33 milliwatts when we're transmitting it to high power. Two versions. The one on the aluminium block is the flight model, and you can see a little bit of blue tape around the edge. I'll explain that in a second. And the other one is the engineering model, which you can pick up fairly happily. The one on the aluminium block, you have to be strapped to where there are straps on your arms and strapped to your ankles. Well, not quite, but everything has to be well earthed, so there's no electromagnetic pulse or electrostatic pulse can actually get into the satellite. As you can see, it's built up of 1, 2, 3, 4, 5, 6, and a couple hidden boards. About 7 boards, and there's a bit missing off the top, which I'll show you the interesting demo later on. But it's a 10 centimetre cube, and it weighs about 970 grams thereabouts. The 2 RF boards, one's a power amplifier, and the other one is the actual transmitter itself, built by 2 radio amateurs. The strange letters and numbers on their call signs, which we are all very proud of if we have them. It's actually the boards themselves are about 900 millimeters square, and the little notch you can see at the bottom.
90 millimeters.
Sorry.
90 millimeters.
About
900.
Yes. Yes, I'm talking a lot. Yes. There are probably about 5 layer boards, I think. I think we went through about 4 iterations of each board as we were designing it over the 4 years. The big block at the top is the interconnect between all the boards down the side. And with that number of pins, trying to get them apart is a bit of a challenge. and then put them all back together again, then take them apart. Oh god! So it's very, very stable. The problem is when you try to stack and unstack them, it becomes a bit of a challenge. What else can I say about that? Again, we're using the I2C for talking across the interfaces between them. Yet another picture of the flight and engineering models. You can actually see a little bit better into them. I think this is a lower level photograph. The bit there, the two big lumps there, are obviously batteries. And it's stacked such that the bits of the satellite which are sensitive to temperature, particularly the batteries, they don't like going below 0 degrees because they're lithium. We have the transmitter right beneath it, within about 1 millimetre of the batteries. So even if it's only dissipating a small amount of heat, it's heating the batteries underneath because there's a big copper plate underneath. I'll show you that when we come to more of the telemetry. The satellite itself is manufactured by a company called ISIS, Innovations in Space Systems, in the Netherlands. So we have an interesting agreement with them, such that they're building it, but the AMSAT-NL member also works for them. So when we have our teleconference on a Sunday evening, we say, "Which hat are you wearing now?" The commercial hat or the radio hat? And it's worked out extremely well. The guys who designed the power board with the batteries on, this is probably one of the, I think it's about the 20th one they've ever built. And it's certainly about the 10th one they've ever flown. So we said to them, how about a discount if we give you all the telemetry that we capture? And they went, sounds like a good deal to me. So I think there is some arrangement with the manufacturers of some of the hardware. Interesting little story. There are two versions of the satellite. I'll come on to I'll tell you that in a second. This is the layout of the satellite, stacked within the 10 centimetre cube. The picture on the top left is in its final state with its solar cells around it on 5 sides. We transmit the telemetry, which I've been involved with heavily. You've all heard me rambling on about the data warehouse. We send data every two minutes, 24 frames, once every 5 seconds, basically, and it's piece of real-time data, and then a payload of some kind. And the payloads have to then be decompiled and rebuilt into something sensible. I shall explain that later, about right at the end. I've said that this is its secondary payload is a radio transponder. There are a lot of frequencies up there. Basically, we transmit on a UHF frequency and we receive on a VHF frequency. And there are 4 satellites mentioned there. FUNcube flight model, UCube flight model, FUNcube engineering model, and UCube engineering model. Well, I'm going to have to back up what I said. Our satellite is called FUNcube 1. The UK Space Agency, God bless them, approached us to say, we need a backup transmission mechanism for our satellite. Would you like to provide that backup mechanism? And we used to went, yes please. So FUNcube 1 became FUNcube 2 as a module within UCube. Space Agency put an invitation out to academia to fly boards on their satellite. We were invited to fly. We didn't have to compete. But I'll show you what UCube looks like in a second.
So they give you any money?
They gave us a small amount of money. Yes, basically, it was a kudos for us to actually put the boards on. So if this works, This is the time, a bit of the time lapse of assembling the CubeSat.
You see the ground strap.
Yes. I won't run it all because it's actually quite a lot of fun. Let's move forward a bit. And you can see it's there with its protective side panels on. A bit of programming, a bit of hardware upload I think going on there. Somebody's building the antenna stack I think on the side. Bit of browsing going, no we don't mention that.
So who's actually doing that?
This is ISIS themselves.
Okay.
So the ISIS did the assembly for us. We're not allowed to do the assembly because we're not space rated engineers.
Right.
So you can see the satellite's there with its solar system. Should we take a look again?
Ooh, high-tech silicon.
Very high-tech satellite. The cap's on.
Okay.
Yeah. It's gone away.
So
Oh, it's back. And as you watch the video, you'll see that it disappears, comes back because they're putting it into their one of the test environments and bring it back to the table again. And you can see they've got a function. You can see, and it's gone through various levels of assembly and disassembly. Don't forget the end of it. Somewhere here. There's a fine. Oh yeah. You can do a quick shot there of a light. Oh, there we go. Light being shot against it. That's actually testing the solar cells. Are we actually getting power off them? And it's in its. There she is. And there she is again in the transport jig. This is a photograph of our illustrious leader, Graham Sherville, who's led us through all this over the past 4 years. This is the only time he was ever allowed to touch the flight model, fully suited up and with gloves on. Mm-hmm. He's allowed to touch the fixture but not the satellite.
Well, it's quite an expensive launch, and then it's quite hard to repair.
So indeed. So this is as she is before. Well, not quite before flight because the antennas are extended. As you can see, a lot of solar cells around the outsides. It's a 10 centimetre cube. I'll show you. And it's basically there are two stainless steel edges and two black edges and two pins sticking out the top. The reason for the different colouring is part of the mechanical engineering science experiment in terms of heat dissipation and absorption. What you can't see behind the solar panels is there are also two silver panels and two black panels as well, for the same reason. I'll show you some of the graphs that come out of it later on. Oh, sorry, I should say the two little buttons, one and one fail-safe. Basically, when the satellite comes into orbit, those will spring out. And the satellite detects I'm in orbit. That's the way it knows. But more about that in a second.
That's a bit like an old-fashioned fridge door button.
Exactly. Yeah, it doesn't like come on. It doesn't come on straight away. It can't come on straight away. Again. I'm not going to play this out. Takes a second. 1, 2, 3, 4. There's a shot in it.
So they're kind of like little reels?
Exactly. Yes.
Okay.
Yeah. What happens is that they are a beryllium copper, and they're learned to be straight. If you heat them at a particular temperature, they will remain straight. There she goes. So 2 long ones and 2 short ones. And we go again.
So they're coiled up in your heat?
I'll just stop that and I'll explain. What happens is that on the top of the satellite, it's the 10 centimeters. It's the square at the top, and in each corner of that is a little box. And inside the box is a little coil, which is the antenna, which is attached to what we call the lid. At the end of the lid, there's a nylon fishing line wrapped round a resistor. You overheat the resistor, it burns the nylon fishing line, and the lid goes ding, and attached to the lid is the antenna.
Is it flight model?
Sorry?
Is it flight model?
That's the flight model.
So they have to kind of put more fishing line afterwards.
Yeah, there is a protocol for actually putting it all back together again. This is why ISIS have to do it. We can't do it. So that was the final firing before flight, and somebody put it all back together again. But we had simulators as well, because I think there's 3 levels of safety. Yeah, if the first resistor doesn't fire, then there's another one, and then there's another one.
So is that a normal sort of spacey mechanism?
Yes, it is for the satellites of its size, yes. It all started with slightly bigger satellites that you're enclosed within the fairing of the rocket. You can't have things sticking out as you launch because they're going to bobble about and hit other things, etc. So imagine you got a steel tape measure. You've all played with them, you've all done that with it and let it spring back. That's the ideal thing. So the earlier satellites, what they did was put 4 of these little tape measures on, non-extended. Before they actually put them in the launch fixture, they just took them underneath, sat the satellite down, and as soon as it came up, they all went ding. This is an extension of that. This is the next step. There are 3 satellites that were launched all at the same time. We were the second one out of the pod. There you go. That's one of the other satellites. There are 3 satellites on board this pod. You'll see in a second this gets picked up and how it gets put into the pod. Lots of gesturing going on. The guy on the right hand side is from ISIS. The guy actually doing the insertion is actually one of the project engineers from this particular satellite. Everybody was given the opportunity to actually put it within the pod under supervision. Very careful. This is an edited version of this, I am told. The first one didn't quite fit the first time. So a little bit of re-engineering had to happen.
On the spot?
On the spot.
Some brought file and...
Yes.
How could we get to this point anymore?
I think there was a small. I think so. Obviously, when they do the solar, when they solder the solar panels, it's obviously bits of wire stick out. It'll probably a fraction of a millimetre, but they wanted the clearance. So they're a bit fetid on the entire thing. So you can see it's the cube size is we call one unit long. The pod itself is 3 units long. Here we go. We're going in next. That's my mate Wouter from ISIS. That's the guy who wears 2 hats. Don't drop it, Wouter.
How do you transfer it to there? How much did that cost?
That's actually in the Netherlands. It's actually done on site at the manufacturer. Very carefully.
ISIS did this big package. Is it their product?
This is the pod itself is actually one of their products.
So
It's the
they-
nicest pod, yeah. So the launch mechanism is actually a commercial launch mechanism. And lots of
If you had to take it somewhere, that would cost almost as much as launching.
the went in a box on a container on a large aircraft out to Russia, and we're all going, please don't drop it.
Mm. Yeah, outside this they just kick it across the floor.
Typical baggage handlers.
Yeah.
Fully
There-
trained.
And there we are in the middle, and the other two satellites on either side of us. It's actually reverse of what you saw.
Yeah.
The lid at the top gets closed once all three are in. And the bit you can see just there, it looks like a spring, is a spring. So once it goes into orbit, the primary payload goes off, and the secondary payload goes off, and the tertiary payload goes off. These guys are paid a lot of money for this launch. So we get it's proportional to the size of the satellite, how much the launch costs us. So what they call and at the bottom there's something called the adapter ring, which is basically what sits on top of the device, on the launch vehicle, whatever it is. And the pods are actually stacked vertically like that, and there'll be 4 or 6 or 8. Once the other payloads have gone off and well clear, after about 5 minutes, they'll open the lid of the pod. The spring will react at 7 kilograms, plenty of energy to push it out, and they just go pop, pop, pop. And on launch day, the Russians were feeding us with a simulation of the launch, and the launch vehicle goes up. First stage, second stage, and third stage actually holds all the satellites. And you sort of think it's going to go up like that and then push all the satellites off the front. It doesn't do that at all. What happens, it goes up, it turns itself in space like that, and then it has vernier thrusters to actually to angle it in all dimensions. And basically, it can point to fire that satellite in that direction, that one in that direction. And we actually had a simulation that once all the primaries had gone off, there was a delay of about 5 minutes, so they were well away, they were tens of kilometres away by that point. Little pod opens, and we could see them going, that's us!
So all three go at the same time?
All three at the same, yeah.
Do they hit each other afterwards?
Occasionally. But there's enough differential, there's enough friction to actually just stop them slightly. And there's a lovely photograph of them being launched from the ISS out of one of their launchers. The photograph is taken just as they're passing the solar panels of their ISS. And I think they've been launched about 10 seconds before, and they're separated by about a metre. What they can tell in the photograph. So there is enough separation. And they will slowly drift apart over time anyway. Okay, so we've this is a preamble to the launch, what we'd expect to see after it. We spoke about the FUNcube dongle. This is a piece of software that's showing the radio spectrum of what the transmitter will look like. The burst of data on the right hand side is the telemetry. Each one of those little bars is 5 seconds, small gap, 5 seconds. So we transmit 5-second bursts of data. And it's actually very obvious when you're hearing it. You can actually hear the. You can actually hear. So he said, "Did you design it like that?" Of course we did. So
that trace vertically. So this is
That's
time,
time,
and
yeah.
that's the gap.
Yeah.
Okay.
and on the other side, the big blob in the middle is part of the. This is an early version of the dongle, so there is a spike part of the how the dongle works. But on the other side of it is another spike, and that's actually a radio transmission. So as well as the beacon, We can also do RF transmissions at the same time. So that'll be somebody transmitting some. It's probably Wouter shouting into his radio. To capture the data that comes down in those 5-second bursts, we have something called the dashboard, written in WPF and C#. One of the guys from BT has written this. He's not very proud of it, but it works. The data this is the real-time data that we get every 5 seconds. So it's basically the characteristics of the satellite for the command team in real time. So we're getting temperatures, we're getting voltages, we're getting how much spin we're getting on the satellite. We're getting a small amount of logic data. Down the left-hand side, have the antennas deployed? Well, we must have because we're receiving it. So there's some redundant data. As you can see, we're running a small amount of energy, talking in terms of tens of milliwatts, in terms of power consumption on board. Are we power positive at this moment? Yeah, we must be. One of the things you have to consider in space is you've got five sets of solar cells. 30% of the time it's going to be an eclipse. So you've got to have good battery power on board and an efficient energy management system. You can model it as much as you want. You don't know until it gets up there how well it's going to be. We are really, really pleased. It's exceeded all our expectations. This is it's not a very good photograph. I'll show you the real version in a second, at the end. This is the what we call the ground. The ground segment is what's terrestrial. The space segment is the spaceship itself. So we call this a ground segment. This is the data warehouse. It's sat in a data center somewhere on Docklands. In terms of hardware, it's a VM running Tomcat and Apache. In fact, there's two. There's the data server, which captures all the data from the dashboard, and this is the second bit, which is the display server. We also have a pair of slave servers for warm start if either of these go down. Various bits of data. This is a representation of what the dashboard has just shown. So it's the engineering power system, the experiments, the RF power amplifier, the antennas, and some of the software flags. Written in jQuery and JSP, and some nice graphing tools as well, which I'll show you later. As we've added more and more functionality to it, so the menu's increased. So we have real time, we have high precision, which is data transmitted once every minute. We have whole orbit data. Basically, when the satellite sends its 2 minutes worth of data, we have a subset of what's happened in the past 104 minutes. So we can get a snapshot, even if people aren't receiving it around the world, what's actually happened in those 104 minutes of the orbit. So we can get alarms from it. You know, has a battery failed? Has something overheated? So we can then go back and look at the real-time data to get more info.
For orbit.
Sorry?
104 minutes for
It's actually 95 minutes for an orbit, but we actually capture the previous bit as well. So we're doing 18,500 miles an hour. If I was stone hard enough, it'll keep going. So we're actually above the International Space Station. There's nothing. There's very little. So there is nothing below the International Space Station. Everything's above the International Space Station.
So if you start spiraling down,
You lit it.
you might catch up with it.
There's always that chance. Our orbit lifetime, our estimated lifetime for the satellite, for the hardware, not for operation, is about 25 years. It'll stay. That's the worst case. It'll stay up there. Lifetime for
Best
the
case, you mean? Free.
Lifetime for the satellite on batteries is probably about 3 years. On solar cells alone, we get another 2 years as well. But that might not happen because we'll get solar cell degradation because of cosmic ray damage. But we reckon we're going to get 3 years out of it.
How long is it there for?
Sorry?
How long is it already there for?
It's been there 56 days. I know exactly. 21st of November at 7:36 in the morning. It actually was deployed.
Those are the dates.
And it's behaving itself impeccably. Okay, so this set of slides was taken, well, it was originally done probably about 6 months before launch. So some of them are talking about, you know what's going to happen rather than where we are now. So we can say November has come and gone. We was like that. Oh, we're going to launch. Oh, we're going to launch. And we knew about 2 months beforehand that we were going to get the launch. But there were some political difficulties in Russia about sort of who was going to fund launches for the next 2 years, etc. So we were on the back of that. You know, we were well down the pecking order of that. FUNcube 2 stroke UCube is scheduled for launch no earlier than February this year. It may slip to June possibly, we don't know yet. This is the launch vehicle, the Telemetry, ex-ICBM, and the charts, you can't see the text information on them. Basically, this gives you an idea of each stage of the rocket and how much vibration goes on. So, in the first stage, it's just basically thrusting. Second stage, there's much more vibration. Third stage, it dies down a bit again. When we had to get space validation for the satellite about 18 months ago, we had to guarantee that nothing would fall off when it got shook with these vibration extremities. So Rutherford Appleton Labs offered us the chance to put it on their shaker table. So it has to be shaking in all 3 axes. So we shake it one way, turn it around, shake it the other way, turn it the way, shake it the other way. We peaked 64 G for a few milliseconds. In the worst case scenario, where the boards are actually perpendicular to the shaking axis, so the boards are flexing like that at 64 G. So somebody said, well, how much is it going to rattle when we take it off? What's fallen off when we take it out of the jig? So took it out of the jig. No, put it on the test rig straight away. Not a problem. So we were quite chuffed with that. So we got space rating for the satellite. When we go for launch, when we launched, I'll revise that. We're launching from Russia, so the launch point is Yasny. We're heading southbound to somewhere over South Africa. We expected to receive the first signals about 26 minutes after launch. Some of our AMSAT South African colleagues, we've been given the early version of the dashboard too. The warehouse is up and running, ready to receive it. We're all looking at the boards and going, please, please, please. I'll show you the little video of that in a second. Satellite comes up in safe mode, putting out a small amount of power. So the guys in South Africa are pointing all their really high performance antennas at it in the general direction it might come in if it's actually worked. And where were we at the time? We were at Bletchley Park. Part of the building there is the Radio Society of Britain's Radio Museum, the National Radio Centre. And you can see on the other side part of the antenna, or one of the antenna arrays, actually not ours, on this, we got too much contrast. Bletchley Park, basically, we all know it for the code breakers. Radio Society of Great Britain about 2 years ago installed their museum. So it's basically a demonstration of amateur radio and radio techniques, etc. And the picture on the lower right is their normal operating room. The public can watch over the shoulders of the operators. And that's what we were going to take over for our ground station. As part of the outreach, we spoke to the National Space Centre, and Anuja has actually done a video for us as part of the outreach, which was shown during the day on launch day. We're trying with the European Space Agency and the UK Space Agency to get education outreach. Over the past 4 years, we've had lots of teachers coming up to us and saying, "Oh, this is a really neat idea." So we turned around to them and said, "Well, what can you do for us?" "Oh, I'll write something for the curriculum." And we've had not a great deal. So we've now engaged with the National Space Centre to do it properly. So we're starting, we're late in the game. We have all the resources available for the teachers to use. We've got all the web, we've got the warehouse, we've got the dashboard, we've got lots and lots of PR information. So Sonia goes to write it, we'll be more than happy to talk to them. Quick update on FUNcube. FUNcube 2, where we are putting 3 cards on board. It's actually a much bigger satellite than we are. It's the 3U satellite, so it'll take the whole of the pod. And in being a bigger satellite, it's got more solar cells on board, more power. So we're quite happy to sit on there, and we can actually get a bit more power out. There have been some problems with this satellite and integration, but that's for another day or in the pub. It's been around a while, about the same time as us, about 4 years in the gestation. It's got more power on board because it's got more solar cells, and it can actually open more solar cells in orbit. These are the same thing. They're sprung open by a piece of nylon twine and a resistor. And they're using the same antenna setup that we use from ISIS with the antenna box on the top. Oops, sorry. I seem to have doubled up my slides or something. Oh, we're going backwards. No, okay. Let's see if this works. This is the launch site on the morning of the 21st of November. I'm told it was very cold by our colleagues at ISIS that were out there. There was a slight delay.
Russia.
Sorry?
Russia near the winter.
In Yasny. Here we go. It looks like a simulation, but it's not. That's how an ICBM would have been launched. On the top of a steam catapult.
That's what that is. Okay.
Yeah. So basically, the launch can be hidden. The ignition happens in a pile of steam. So what happens is, the steam ejector pushes up about 100 feet in the air.
And then the rocket fires.
Then rocket fires and blasts the plug.
Because you can see it. I mean, it kind of goes up, slows down, and then fires.
Yeah.
It's better than having
And basically, and that's all a passing satellite would see, would be a hint of steam and a load of dust.
Probably quite a strong hint.
Yeah, I think they know what to look for. Okay. So, our South African colleagues picked it up exactly on time. We were watching the big board. And somebody saying, when do you expect to see it? Oh, about now. Stage. So we had our first glimpse of it arriving over to South Africa. We saw it about 9:30 in the morning, but it's very, very low on the horizon. And we could just detect its signal. We couldn't decode anything. The next pass was about 11 o'clock in the morning, but it's much higher. And the decision was made, shall we try and talk to it? What a stupid question. Well, this is what happened. Not got any sound. Oops. Right.
No. Your volume's too low.
Yeah. What had happened there was we'd sent a command, it was running on low power, we sent a command to it to come up on high power. And basically, yeah, do we send it, don't we send it? Send it blind. So Wouter just in the corner there, hit the button, and basically just comes, it's just a set of audio tones and encryption that go up the satellite. It takes about 5 seconds for the satellite to detect that. Is it really us sending it? Yes, it is. Do some encoding with the satellite to do a lot of latches. 5 seconds later, she came up in high power.
Well, we expect you to send some kind of backup command first.
We just wanted to play with it. So you can see that a lot of the team, there's about 4 of the main team there, and everybody sat in the background. There's a lot, the joke amongst the project team is that the project is supported by Bollinger and pork scratchings. We had a meeting in Kenilworth a couple of years ago, and one of the guys went to the bar and said, "Is the restaurant open yet?" "Sorry, not yet." "Okay, well, I'll have a bottle of Bollinger, please. And what food have you got?" "Oh, we got some pork scratchings." So we had a meeting funded, fed by Bollinger and pork scratchings. And the other thing is that it's also funded by Jelly Babies as well. So whenever there's a project meeting, there's a huge bottle of Jelly Babies on the table. So one of the thoughts was, you know this bit of the story. Could we put a Jelly Baby inside the satellite? Gary suggested that we could actually 3D print a sintered version of it. Maybe the next one.
I do have a lot of contacts in 3D printing.
Right, and this is something else that happened. Again, my apologies for the... come on. Have we lost the network? We've lost the network.
Maybe. Oh, yes.
Such a shame I got sound. Okay. This the second day we were there. Nice shot in my back of my head. We were approached by the BBC, care of Bletchley Park, to say, "Can we come and film you on the second day?" And they came in and said, "We're not going to interfere, we'll just sit in the background and film. We'll make something of it at the end." And they were there for 6 hours. Then they must have filmed for at least 4. And this piece, which is probably about 6 minutes long, went out on BBC Breakfast on the Monday following. It was 6 minutes, and they've been filming for 4 hours. And I want to come on the desk at some point and actually listen to it properly. We were really pleased with the way they did it. There was no, well, the thing about radio amateurs or the radio ham in the States, we do get the mickey taken out of it a little bit, but they did this really professionally. We were really, really pleased with it. This is Graham doing his piece to camera about satellite. Yes, we did have to wear the t-shirt. But you can see in the background, and this is my colleague Kieran. They took us into a school in the afternoon as well, so we didn't know anything about going to the school, and the school only knew about us going in about 3 hours before as well. The kids are brilliant. Asking, completely, they didn't know anything about this, but the questions they were asking were really, really good. And Kieran does a lot of scouting, so he's used to sort of talking at this age group, and he did extremely well. I invited him here today, but unfortunately he couldn't make it. But we were really pleased with the whole thing and the way the BBC did it. And we were talking to them at the end of it and said, it's going out on Monday, so you've got this 6 hours to condense into how long you're going to do it. So you've got to take this into an editing suite. Oh no, come and look. And they've got this big RV, well, not a medium-sized RV, drive with blacked out windows, opens the sliding door, and there's the video suite in the back of the van. So as they're driving along, they can be video editing at the same time.
You need an apostrophe there.
So this is our usual part of our pitch. We like to be able to get involved. We're looking for STEM ambassadors. And radio amateurs send their telemetry and use the transponder. And so far we've had 600 people register to upload data to us. About 450 people have been uploading data. We average 5,000 packets a day coming into the warehouse, and it's going up, which is what we didn't expect. We expected to have the initial enthusiasm and it to tail off. It's a steady trend upwards. So it's gone extremely well. If I can now try and do a live demo.
Yes, that's a risky thing to do.
This is a risky thing to do. Okay. So this is the warehouse in real time. Let's get the last packet was received at 13:58, which looks about right to me. We might get another packet. They come every 10 seconds if we're receiving data. So we've probably gone out of range of this station. We should be coming over the UK in about 10 minutes, but looks like we're going to be unlucky. Basically, this is the set of data that's on the dashboard main screen. So it's the solar panel voltages.
But it must be in daylight.
This is in daylight. Yeah, we have a differential between how much current we're getting off the solar cells, how much current we're taking within the system. So we're positive by 150 milliamps. So we're charging and using. Temperature internally is probably about -4 degrees, something like that. There's a bit of offset from sensors. Sun sensors basically, on 3 of the sides we have basically a pinhole camera that's looking at the sun, so you can actually see it as it passes, what spin rate is in any axis. Solar panel temperatures, we're down at about -18 on the outside of the satellite. We're getting live data. We're getting live data from somebody in the UK. That data provider was that who provided that last packet, and there may be more people. If we stay about for another 30 seconds, there'll be more people sending data, and we actually record the fact that the providers with data, but we dedupe. We only restore one record. Yeah, so there's somebody in Sweden. So we've had 41,000 2 minutes worth of data. That's about 470 from the original. So we've got the high res, which is once every minute. Scaling is a bit off, but this is Jason feeding a graphing system. I'll turn some of these off. You can see how they've also changed during the past minute. So we're actually getting an because we're obviously we may be coming into sunlight when that was captured, so we're getting more volts. Whole orbit data is, as I said, it's the last 104 minutes of data. Oops, get it off there. You can see from the centre line that it's a bit blocky. The centre bit is when we're in sunlight, and the other two downs are when we're in eclipse. And this is the temperature of the satellite decreasing, coming to sunlight, temperature increases, temperature decreases. Not quite enough time to show the mechanical engineering experiment. We can actually see the ramp up of temperature and decay, and it is different on the silver surface and the black surface as well, so we can actually show what it looks like. Fitter messages. Somebody's been uploading stuff this morning, I think. We always like to say thank you to our sponsors. Well, thank you for people who've been uploading data to us. On there, we did some STEM outreach last Friday at Bletchley Park. We like to tell the world about the facilities on the satellite. And one of my other colleagues, thank you, did a small map for us. So we can actually tell in real time where the satellite is. There should really be a small sort of circle around the satellite, which is basically what the footprint is, what you can see. So basically we're just North Atlantic, and probably the edge of the footprint is just touching the site, touching Europe. And the dark blue and light blue, dark blue background is when it's in eclipse, and we're just coming into sunlight now. But because the satellite's so high, it will have seen sunlight before we see it on the ground. People like to see how they're scoring. So this is the list of all the people who have sent us data. We thought about giving the top 10, and somebody said, how much more effort is to tell us everything? No more effort. Some people have got a fair number, but they're actually fairly far north, so they see it more often than the rest of the world. If you're polar, you see it more often. So there we go. That's FUNcube. I hope you enjoyed the presentation.
Thank you.